Python's interpreted.
So
but
wait, I just had a thought.
Yes.
Because computers speak binary.
Yes.
Do they also speak code, or is code, like Python, is that a middle translation? Is that like translating English into a code that the computer then translates into binary?
So languages, there are high-level and there's low-level languages. All languages are a way of a human expressing to a computer what they want to do.
Yeah.
If you're down at assembly level, assembler code, you're actually telling the computer specific instructions of read this register, read this memory location, load it into this memory, load it into this register, and provide this operation on it. And they write that in embedded devices where they need really minimal, small, and extra fast, real low computing power. And so the computer doesn't have to do any work. It's kind of a machine language assembly code is kind of as close down as you normally would get to the computer. Mm-hmm. And that's a low-level language. But then you go right up to high-level languages, and those high-level languages, provide a lot more nuance.
Okay.
But ultimately, it all ends up. So Python, there are compiled languages and there are interpreted languages. So C++, I don't know if you've heard of any of these things. Java. Oh, Java. No, Java is an interpreted language. Java has a runtime library, and it's a piece of code that knows how to read Java code and turn it into something the computer can work. And so you start up, and the reason why they did that and why Python is what it is that then you get the Java runtime library for Windows, and it knows how to take exactly the same. The Java remains the same, the code you write, but the way that it has to run on a Windows computer, it knows how to get a Windows computer and put the Java runtime library for Apple onto an Apple, or Android onto an Android, or Linux, Unix. If you have the right runtime, you can write one piece of code and it'll work anywhere. Whereas if you compile code, it runs fast because it doesn't have to be interpreted on the run. Right. But computers now, for a lot of things, are fast enough that the overhead is not so bad. When you're talking about back in the day when we were running 486s with 1 mega RAM or less, 640K, as famously Bill Gates said, who's going to need more than 640 kilobytes of memory? And then had to write high-mem.sys for DOS to push up to 1 meg.
That's very funny.
But at the time, you had the Commodore 64, which was 64 bits. Yes, things have moved on.
Right.
And so, what was impossible and ridiculous.
So back in the day, it kind of used to work like what I was saying, but now it doesn't so much.
Well, it still does. I mean, ultimately it does. But what you can ask a computer to do and expect an answer this century has changed dramatically. You look at the number of instructions that a CPU can run, and the amount of memory you can have available, and the amount of, you've got random access memory, you've got ROM, read-only memory, you've got hard drive, permanent, you've got memory that volatile and involatile memory. So there's volatile memory is stuff
I know this much. Memory is RAM.
Exactly. Yes, for those that know. But you have memory that's really fast, and so that's your RAM is really fast, and a solid state drive is faster than a hard drive. Okay. Where you have a disk spinning around with heads reading it, and that's faster than a tape. Right. And that's faster than punch cards.
I forgot about punch cards.
And I actually worked on machines. I'm actually a machinist, fitter machinist by trade, and I worked computer-driven machines. And when I first started this company, they were still running paper tape. Oh my goodness! And I convinced them to get a computer. Anyway. I mean, they had computers, but the computers were slow, and the memory storage was 8 holes on a punched-in rows.
That's wild. I can't even begin to understand.
All right. Now, actually, that leads me to... We'll come back to that. All right? But I think it does matter, and this is where... this is me, and I'm going to say straight up, are we going to end up with that?
It'll be fine.
I honestly believe that if you're going to play coding, it doesn't hurt to understand some really basic stuff. Because then there's a lot of terminology that comes up, and if you're trying to write Python, you're going to get errors, and they're going to come up and you're going to go, what on earth is an invalid indirection or something like that.
Well, I mean, before when you were saying that, you know, there's the programs for the artistic ones who are, like, it saves you from a lot of the nitty-gritty of the coding. It does sound to me like it would be handy in some capacity to know how it's working underneath.
Yeah, I really think so. So, what do you know about binary?
Ones and zeros. There are 10 kinds of people in the world. Those who read binary and those that don't.
There are 1-0 kinds of people.
It's a whole
You understand
and
that?
a not a whole.
You understand that joke?
I do. You explained it to me once.
Well,
Yeah.
so,
I mean, yeah.
all right.
Because it's the...
So all we have to store things, everything has to be, and you've heard the famous thing, it's noughts and ones, right? Everything's noughts and ones.
I haven't, but
Oh, all right. Well,
I appreciate your faith in
I'm
me.
sorry, your ignorance is astounding to me. So, noughts and ones. So how does everything come from noughts and ones? So, let's say we start with a byte, right?
Great. I've seen that word before.
Right? And then you've probably seen kilobytes and megabytes.
Gigabytes even.
And terabytes and petabytes.
If you're very lucky.
Right. So, what is that? A byte is 8 switches.
Oh, okay, yes, alright, yes.
So we got 1,
I'm getting memories.
2,
I was in high school when you explained this to me.
right, 1, 2, 3, 4, 1, 2. So we got 1, 2, 3, 4, 5, 6, 7, 8. Correct. Right? Now, that is just 8 switches. But if you turn this switch on to 1, it adds 1 to the total.
Yeah.
If you turn this one on, it adds 2. 4, 8, 16,
And that's,
32,
I can explain the joke.
64, 128.
Ooh, can I get it right? So if the switch is, because on off, right, is a line and a circle. So 1, 0. This is me thinking. So if this one's on and that one's off, then it's 2. So
Correct.
it's 2 kinds of people in the world.
Correct.
I knew that was it, but like now.
So
it makes
if
a
you
lot of
go
sense.
1, 0, 0, 0,
So
0,
the circle
0,
is off
0,
and
0,
and the line is on.
well,
On things?
that's a 0 and that's a 1.
Right.
Right?
But I'm just saying, because where's that vacuum cleaner I had? Because on machines, it's
Yeah.
the little line in the circle.
Yeah, it's based on
So is the 1 on and
the 0's off. And there are standards. If you go online, you can find standards that have all the things for all the different standby and everything. There's actually a standard, and it's all based on this sort of stuff. So you can actually, if you know that,
so
you can read
knowledgeable.
any set of switches that are done by that. All right.
Gotcha.
So this is the noughts and ones we call binary because there's only 2 states.
On or off.
Binary. Right? But we can say it's also decimal. Right? And that one, binary, it's 0, 1, and we start
How's it decimal?
rightmost, right? 0, 0, 0,
Wait,
0,
how's it decimal?
0. And decimal is base 10,
Yeah.
right?
It's base 10, but there's 8 switches. And
is
they're
2.
All, this is 128. No?
Right? So 1, 0 binary equals 2 decimal. Why are you looking so confused?
Because what does that mean? Why does it?
Okay, so decimal.
Why does it equal 2 decimal?
Because decimal, we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Naught,
Yeah.
1, 2, 3.
Yeah.
So that's 10,
Yeah.
right? So there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 states. Deci is 10.
Yeah.
So then you go 11. But binary, you go, if you go 1, 0, 0, 0, 0, 0, we'll stop doing all the zeros, equals 1. If you're counting normally, that is equal to 1, and that is equal to 2.
Okay, so it's called deci. It's decimal, but it's
Which
not
is
like
norm-
but it's not like in tens. It's just normal counting.
It's normal counting.
That's just what normal counting is called.
It's decimal.
I mean, I knew that we were like decimal based, but like, okay,
Right,
all right,
that's
I'm in it. Okay, I
Now,
get it.
I won't go deeply into
You know
it.
how I'll make myself think of that? I'm gonna, because really, 1, right, is, this is a stupid thing to say, is 0.1 10 times.
That's true. Well, that's what the whole
That's how
thing's
I'll think
based.
of it.
Everything's based on that.
Right.
But that's because we've been taught to think in decimal, except when we're doing time,
Yeah, which...
where it's 12 and 24, and there are in degrees it's 360 and 45,
right.
and you know. So there are a lot of places where we use non-decimal. But when I was at school, I rebelled in 3rd grade and refused to do my homework. And I remember Mum was sitting there just desperately trying to deal with the fact, actually sitting outside of school trying to make me do the homework. And I'm going, but what does it matter if it's 1 plus 1 equals 2? And if they tell me, and it was actually, if Mum had been able to say to me, actually, but think about time and how it goes to 12, I would have gone, oh. But no one said that to me, including my school teacher, and I rebelled and pushed against it. So, right, hexadecimal matters too, and octal. So, what is 1 plus 2, actually, 1 plus 2 plus 4 plus 8?
I'm doing it, just give me a second. It's 15.
That's right. So, if we go down the line there, right, we split that up into 2,
Yeah.
and that's what you do a lot of the time, right? If you want to, rather than, that is getting hard to get a head around.
Right, because there's big
Because there's
numbers.
some, yeah, now that's 0 to 255.
Right,
This is 0 to 15, which is 16 states including the 0.
yes.
So hexadecimal is 0 to 16. So it is 0 to 9 and then A
0
to F.
Why A to F?
Because A is 10, B is 11, C is 12, D 13.
But why do we swap them to letters?
Well, because you need to be able to say, so you have 0 to F in hexadecimal. So you go 9A, B, C, D, E, F.
So you can't use double digits.
No, because
So instead of
it's
going
based
into double
on 16.
digits, right? So instead of going into double digits, you swap to letters.
Yes, and so if you have 1, 1, 1, 1, you have 1 plus 2 plus 4 plus 8,
15.
which is F,
Okay.
which is 15 decimal, which is 1, 1, 1, 1, 0, 0, 0, 0 binary.
Okay.
Right, they map.
Right.
And so hexadecimal 2 is 2 because it's less than 10.
Right. Ha. Okay.
But if you go
Oh my gosh! Wait.
1,
wait.
0, 1.
Wait. When we say hexadecimal, don't laugh at me for saying this. How does that relate to when? Okay. Colors have hex codes.
Yes.
Is that related to?
Yes.
That? Okay, great. That's all I needed to know.
And you'll see.
And they use F's
and B's
yes,
and
yes, there'll be this.
And
it's-
how
and
many-
the numbers and the letters,
how
but
many-
it never goes. Okay.
how many bits? Like if you got 64-bit color,
Oh.
then you need how many bytes?
Ah.
A byte is 8, so you need 8 bytes to represent 64-bit color.
Ooh.
And that gives you 0 to 64,535 colours.
Colors. Wow. Okay. All right.
Right? So this, when you look at all those things, it'll be, if for a byte, they'll say it's 2F.
Right.
So what does 2F mean? Yeah. No, I just did that wrong. A colour, if you say that a colour is to, you know, see, it'd be blocked into blocks of, so that's, if you look at your colours.
I'm gonna pull up a hex code for a colour. I'm gonna hex code aqua. That's what I'll type in. And it'll just give, oh, well, it's not a very exciting hex code, but it says hash sign.
Yep.
00.
Alright, 00.
F.
F. Right? So, each one of these is, each letter of this is a nibble. So, 4 is a nibble.
Okay.
Right? Is 4
right.
bits.
Because it's half a byte.
Just half a byte.
Okay.
Okay. So, to represent 1 byte of data,
okay.
you need 2 characters.
Okay.
So you need 1 for these 4 and 1 for these 4. So 00 means that the first byte, there is 3 bytes, which is 24-bit colour.
Okay.
Right, because it's 3 times 8.
Mm-hmm.
So there's 8, there's 8, and there's 8 bits. So multiply them, that's 24-bit colour. Right? So we'll write that down, 3 times 8 equals 3 bytes. Right? That all makes sense?
Yep.
So in this case, this colour is 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1. Oh, it's actually 0, 0. We got another 4. Right. There we go.
There we go.
1, 1. So there's your first byte.
There's a byte.
1, 1, 1, 1. 1, 1, 1, 1. Second byte. And 1, 1, 1, 1. 1, 1, 1, 1. Third byte. That is what the computer stores as a set of 24 switches, 3 bytes, to define that colour.
I feel learned.
Right? And so if you wanted to take a slight shade off that, and what it breaks down, it actually breaks down to RGB, red, green, blue, and then there's brightness and hue.
Yeah.
So
I've seen that on Photoshop.
So this information is actually broken up into sectors, and this bit of it represents the red content, this part, the blue content. So it's so many bits, so many switches represent this part, the red. So many represent.
When you're on like an art program, they're breaking down the RGB. They have them as separate like scales, but they do them in. And so you like
end up with a hexadecimal.
It's just representing it visually, and then you mix them together.
Yes.
Okay.
Okay.
Cool. Okay.
So
hexadecimal, right?
That's why hexadecimal matters, is because hexadecimal gives you a way of, you know, if you had to write this down to represent your colour, you'd be going nuts.
Yeah. Yeah.
But at the bottom level, and I have to look, I have looked it up in the past, but you'd have to find out which components of these are, you know, you need R, G, B, and then brightness, and bright, and hue, right? So I can't remember exactly how they break up the 24 bits for a standard 24-bit colour, but it's that. It's broken up into sections, and these bits here tell you red content, these bits tell you green, these tell you blue, these tell you brightness, these tell you hue, and it's designated as a colour, ASCII colour. The hash just is an instruction to say, what I'm telling you now is an instruction about colour. Now, if you then go to so now we understand that. Okay, so we've seen you've tweaked a colour. What about letters?
No idea.
So you have the ASCII chart.
I never would have guessed that that's how that would be spelled.
American Standard, something or another. It's a, I can't remember, might not even be American Standard, but that's an acronym.
Right.
From some institute that defines.
Gotcha.
No. So in that case, a character has got.
As in a letter.
As in a letter.
Of the alphabet.
Not as in a part of your game. A character is represented, it used to be by 7, and then they made it 8 bits, right? So if you cut that off...
Why did they decide to cut off the 8?
Oh, because back when they were doing this, you had text mode screens, you had 64K of memory, you had every instruction. So you remember I was talking about that punch tape?
Uh-huh.
So you've got a piece of tape here, and it's got holes.
Yeah. I've seen those in the movies.
Right. So that could have been done neater, but each of those holes, that is your 8 bits.
Yeah.
And if there's a hole there, it's a 1, and if there's not a hole, it's a 0.
Wow, that's an interesting choice. I would have gone the opposite.
Well, the reason why is the way it's made is you have your tape in there, and you've got a line of lights along here. Each one of those is a light, right? And on there here, you've got a bunch of receivers.
So if there's a hole, the light is on.
Yeah, and that turns to
if
1, and if there's not a hole, then that's a 0.
Effectively makes the light off. Okay.
Right?
Yep.
So as the tape runs through, you've got these
That's very clever.
light-sensitive diodes that pick up, and you've got light-emitting diodes on one side, like photosensitive
and that's why
diodes
in
on
all
the other.
the old Doctor Who's and things in Blake 7, it's all flashing
Well,
lights.
that's because it looks good on film.
Yeah, but I choose to believe that it's because that's how computers worked.
And I'm completely ignoring someone using
Do you
a
want me to shut
pretty
the door?
serious saw over
It'll
there.
get stuffy, but I can shut the door.
So, ASCII, if you Google on your phone, ASCII character codes.
ASCII character codes. This is the theme song.
And then in, go, and then click on that. Here is, and I will insert a page grab of that.
Yeah.
But here are the characters. So if you want an uppercase A, it's 41.
Okay. Oh, hexadecimal 41.
You can see it says decimal hex char. So that's the character. Right. So if you look at that chart, you can see that there is a decimal number for each of those.
65.
So
space
character is decimal 32, hex
That's
20.
wild.
Right? And so you go down here, P is decimal.
What do these mean that say...
Null, start of heading, end of text. So you need instructions. So if you got something, you need a null character is something you use to say it's nothing. A line feed is like, you've got carriage return line feed. So going back onto the old typewriters, when you went like this, it did a carriage return, took the carriage back over, and then it did a line feed. It was two things. The first thing it did is took the drum right over, and then it rolled up to the page up.
Right.
So there's a carriage return and a line feed, and so there's carriage return is in there as well. So if you want a new line on Windows, you get a carriage return line feed, whereas if you're on Mac and Linux, you only get a line feed.
Oh.
So, I mean, line feed or character return. Anyway, it's different. So when you're moving files from one format to another, you have to make sure that you deal with the end of lines, because the end of lines are different between different file systems. But anyway, so you can see here that they're 0 to 127, which is 128, right?
Yes.
Right?
I do understand that, but it is a very funny sentence.
But if you now go back and go extended ASCII character, so now you need extended.
Extended.
So that's if you have 7 bits. And if you've only got a small amount of memory, that 1 bit for every character in a piece of text, and you've got a long piece of text, you save a lot of characters, which means you use a lot less memory.
Right.
So you'll notice that down in above 127, there's a whole lot of weirdo looking things, and some of them you'll see in there. There's like this one here at there's your OX is hexadecimal. You got this one here, which is 171 decimal, is this. and there's another one that's that, and there's another one that's that, and there's another one that's that, and that, and that. And what it means is back in the day, your old DOS computer had forms. I'll just draw on your land. And so those forms look like this. And then you might have 2 lines down here, and 2 lines down here, and then a line across here. That, you say, I want
that
one
is
of these...
tartan.
All right, but what is it? Is you say, I want a character like this, and you put that there. And this was 80 characters, and that was by 25.
Okay.
And so you go, I want that on this corner, and I want that on this corner, and then I want this right across.
You know what it's like, honestly? It's like
and then I want
making
that,
a custom path on Animal Crossing.
Yeah.
Because you need to account for corners and you need to account for...
And so in that extended set, it gave the people with one more character, they had enough, by adding one more character, you double the number of states you have. Every time you add one, because if you add one more, you add 256. And now you've got 512. And if you add one more, then you add 512, and then you add 1024, 2048. And so it gets bigger and bigger, and so you get more...
2048 was a game where you had to... It doesn't matter. Go on.
So you could... And I actually played with this when I first started programming. I did it in DOS. And you just drew up forms. Just use 80 by 25 screen resolution. And you had this ASCII character set, and you just say there was a function that you'd say draw this so many times, and it would just write it out. So you didn't have to write this one out, in a loop. In that case 78 times, because you got one like that, and then you got these one in the middle. Yeah. So you could draw up forms, and then inside of that you could write your text, and have name, and then over here, and it'd be Andrew. Right. And so you could create these forms, and if you look at the old DOS forms, they were all using this extended ASCII character set to make, to draw up the screen, all the squares and stuff. Right. So